Here's a tutorial for lift formula problems 6 through 10. Again, we start with a basic lift formula using density ratio for air density and velocity in knots for the velocity. We're also going to use load factor. Load factor is lift divided by weight, or G's, G loading. And load factor related to bank angle can be found through basic trig, but it's load factor, the M, or the N rather, that symbol, it's a Greek letter, is equal to the reciprocal of the cosine of the bank angle. For problem 6, we add a load factor in here. We want to find stall speed, so the first thing is to take the lift formula and rearrange it to solve for stall speed. And I added a load factor in here because the load factor is equal to lift divided by weight. Since load factor is equal to lift divided by weight, then we can get the total amount of lift by multiplying weight times load factor, which is what I have done right here. Now we're going to want to simplify this formula. Where we get the square root of both sides, and when we do that, we eliminate the velocity squared on the left side, and so we wind up with this particular formula. Now we'll substitute in our values, or we'll place our values in, our known quantities in. And now it's a matter of simply solving for velocity. And the new velocity, the stall speed in this case is going to be 92 knots, and that will be in true airspeed. Problem number 2 is a load factor change. What happens to stall speed when load factor changes? We set up the lift formula, cross out what we don't need in the lift formula, here I've taken the velocity squared, moved it under the lift, and that's for condition 1. Is equal to the condition 2 parameters, that is stall speed of the airplane. This is in the first condition. Load factor of 3 is in the first condition. Stall speed at a load factor of 2, which is second condition. So condition 1, load factor, or lift, divided by velocity squared of condition 1 has to equal the load of condition 2 divided by the velocity of condition 2. Solve for the velocity of condition 2. So that isolates, that algebraic manipulation isolates velocity squared of condition 2. Now we need to simplify the formula, getting the square root of both sides, and by doing that, that eliminates the squares, the velocity squares of the in the formula, so it makes the formula easy to work with. And then plug in the values, and we wind up with velocity, the new stall speed, going from 3 Gs to 11 Gs, the stall speed would go from 42 knots to 80 knots. This problem is very similar to the previous problem in that a published stall, but what you have to know is that a published stall speed will be given at a load factor of 1. So otherwise it's the same problem as the previous one. We set this up. We have for the first condition is it has to be equal to the second condition. Unknown in the second condition is the velocity. Algebraically manipulate the formula to isolate velocity condition 2. Clean up the formula by eliminating the squares, getting the square root of everything. Allows us to isolate the velocities. Plug in the values, and we see that a 42 knot stall speed, when we go from 1 G to 6 Gs, will give us a new stall speed of 103 knots. This problem is similar to the previous problem, except that we have to determine what the load factor is at 30 degrees of bank before we can solve it. So we know that load factor is equal to the 1 over the cosine of the bank angle. So the reciprocal of the cosine of 30 is equal to 1.15. Now the problem is the same as the previous problem. Set it up. Solve for velocity, the second velocity. Clean up the formula. Substitute in the values. And we wind up with a new velocity of 44 knots. So at 30 degrees of bank, the stall speed will go from 41 knots to 44 knots. This problem is really a true airspeed problem. This is one we would work on our E6B to find true airspeed, starting with equivalent airspeed. Of course, to get to equivalent airspeed, we first go to indicated airspeed, then we go to calibrated airspeed, and then we would have to go to equivalent airspeed. And this would be an airspeed range where equivalent airspeed would be a factor. So the first thing, of course, is we start with the lift formula, and we eliminate everything that we don't need out of the formula. And so what we need is density ratio versus velocity. We set up our two conditions. Condition 1 of velocity and density ratio. And for sea level, density ratio is 1. And now we manipulate the formula so that we first isolate velocity of the second condition, then we simplify the formula. So we wind up with velocity of the second condition is equal to the velocity of the first condition times the square root of the first density ratio divided by the second density ratio. So we set up the formula, plug in the known values, and solve. And so we would wind up with V2 of 590 knots from an equivalent airspeed of 349, and that 590 knots will be in true airspeed. This is the number you would get if you worked it on your E6B. Okay, Okay, now we've added the category of aircraft in here, figuring what VA is. VA is the stall speed at which the airplane will stall at its maximum rated G loading, which is, for the normal category airplane, is 3.8 Gs. So it's similar to other problems. We're going to start with the lift formula, solve the lift formula for velocity, simplify that lift formula so that velocity is equal to the rest of the lift formula. The new wrinkle that we've added in here is load factor of 3.8 because of normal category. So we're simply going to increase the gross weight of the airplane by the load factor, which is the lift that the wing will have to generate at 3.8 Gs. So now we're going to simply plug in the known quantities into the formula. And we wind up with a VA now of 83 knots. Density ratio is 1 because it's given as 1, but these are sea level conditions normally. So the VA for this airplane would be at 83 knots. And I included problem 11, and that's farther than this tutorial really goes.